Good evening, everyone, and welcome to the October meeting of the Ottawa Centre for the Astronomical Society of Canada. We've got a great program for you tonight. We're going to have our usual suspects, Dave Chisholm giving us Ottawa skies, Al Scott with his 10-minute astronomy news. We're also going to have Paul Klauninger giving us a report from Imager's Corner, a product review on the lens-based purchase. After the break, we have a very special guest, Leech from CCERA. So it'll be an exciting talk on radio astronomy. It'll be followed by observations and various announcements. And also, happy Thanksgiving for those of you who will be celebrating that this weekend. So we've got, these are our new members this month: John Albert, Donald Clerk, Ari Good, and Dave Ham. Welcome to the RASC. Thank you for joining us. We've had 46 new members thus far in 2018. That's fantastic. All right, so I'm going to start out by handing the podium to Mr. Dave Chisholm.
Well, good evening. It's great we finally have our monitor working in front of us here, so I'm not constantly turning, so that's great news. Okay, so let's take a look at the moon phases for October. Full moon is going to be on October the 24th. I have 3 comets this month. It's a busy month. So first one is Comet 21P Giacobini Zinner. And these are a bit of an eye chart. It will be in Astronauts, what I've got up here. This one is at magnitude 7.6, and this is its path right here. And this is starting October the 5th for this particular diagram. The next one is Comet 38P Stefan Orterma, sorry. It's pretty dim right now, magnitude 10.6. There it is, October 5th, and then moving forwards. The next comet is Comet 29P Schwarzmann-Walkman, and there we go. And this is a path right here. So it'll be visible right through November as well. Apparently it went under a bit of a bright outburst around September 20th. It was 13th magnitude. It's now magnitude 12 in brightening, and it's about 20 arcseconds across. We have the direct meteor shower, and it's a fairly minor one, 10 meters per hour. And it's actually produced by the dust grains left behind by Comet 21P Giacobini Zinner, which was first discovered in 1900. This one is good because there's no moon, so it'd be excellent viewing this month. Unfortunately, the next one is during a full moon. And this is a busier meteor shower, 20 meters per month, and this was created by remnants of Halley's Comet. And that's October 21st and 22nd. In terms of planet viewing, Mercury is not visible. Venus is not visible. Mars is visible all evening. Jupiter is visible first part of the evening, first half of the month. By the end of the month, it's setting too early. Saturn is visible the first part of the evening. Uranus is visible all night. And it's at opposition, which means it's closest to the Earth on October the 23rd. Neptune is visible all night. And there's your cartoon for the month. Thank you.
All right. Thank you so much, Dave. Al, I think you're up next.
Good evening, everybody. So, it's been a while, so we're back with the 10-minute astronomy news. So I got a few items tonight, nothing major, but a few interesting little bits to show you. So first, I'd like to talk to you about a amateur supernova discovery from 2004 that was discovered in 2017. Interesting, you say? Stockler de Moraes was imaging the galaxy NGC 1892 with his 12-inch scope, and later wanted to compare his image to an archived image. So you can see over here, here's his nice image with his 12-inch scope. So he pulled out an archived image from the Carnegie Irvine Galaxy Survey from 2004. This is the image he pulled out. Compared the two, and he noticed that this wasn't here. So he called up an astronomer and said, what's going on? And they looked back and they checked for planetesimals and stars, and well, he discovered a supernova that was in the catalog. The transient was absent in all other images that they searched, so this is the only image they could find of it. So they assume it's a type 2P supernova, which is caused when the core of a massive star suddenly collapses, I guess due to the short transient nature of it. So it's an interesting way to discover the supernova. This one is a new trans-Neptunian object, was detected by Scott Shepard. You can see the discovery image on the left, and the picture of its orbit on the right as compared to the solar system. So you have the giant planets over here, the Kuiper Belt. Here's Sedna, which was the most distant large one that had been discovered up to now. And this is the one that he's discovered. He's nicknamed it the Goblin. This is actually an inner work cloud object. The closest it gets is about 65 astronomical units to the Sun, or just under twice Pluto's closest approach. So it doesn't ever come inside Pluto's orbit. And it goes out to something like 2,300 astronomical units at the far end of the orbit, which is basically inside what astronomers consider the inner Oort cloud, which is kind of where the long period comets are thought to come from. Interestingly, the orientation of this orbit continues to support the idea that there might be a massive planet somewhere out there, because it's on the same sort of angle as the other planets that have been planetesimals that have been discovered. They estimate it from its brightness, it's roughly 300 kilometers wide, roughly the same width as Saturn's moon Hyperion. Extrapolating from these objects, the three objects now known to grace the inner Oort cloud, and the sampling that they've done, the team estimates that this largely unexplored region of space might harbor roughly 2 million bodies wider than 40 kilometers. So, roughly the same mass as the Kuiper Belt. So an interesting discovery, and stay tuned, I'm sure there'll be more based on the numbers. The last item is about the interstellar interloper called Oumuamua, the strangely elongated body which came through the solar system on a hyperbolic orbit and is heading back out to interstellar space. It's highly elongated, cigar-shaped. I think it's something like 800 feet by 100 by 100, roughly speaking, based on what astronomers measure. And it's tumbling in about an 8-hour period. It first entered from interstellar space and flew through past Earth about a year ago. And in the aftermath of the discovery, astronomers have been reviewing their observations and trying to find out more. Right now, it's beyond 30th magnitude and out past Jupiter, going past Saturn probably in January. In June of this year, a team of astronomers announced that some force was slightly changing its orbit. And they believe the most likely source of this was either ice or gas erupting into space that was otherwise invisible. There was no sign of a cometary tail. However, spectra suggest it may have ice on the surface. However, if this object released enough gas to change its own trajectory, it should also be spinning up due to its long aspect ratio. It's unlikely that it's emitting it from the center of mass, just because of the size or the shape of it. So a bit of a mystery as to how it's accelerating without spinning up faster than it's going. Another team traced back its orbit and tried to find out what star system this might have originated in, whether it was one that's nearby, for example. So they presumed that it's accelerating on its own based on observations that they have and tracked it back, comparing it to observed positions and motions of over 1.3 billion stars from the Gaia catalog, on the second release of the Gaia mission. They identified 4 dwarf stars as the most likely candidates amongst that group. However, none of them had a predicted extremely close pass in the past. The stars were mainly chosen based on similarities between their speeds and that of this object. Because astronomers think that these objective objects probably don't leave home at super large speeds. The best candidate is a red dwarf star called HIP3757, and Oumuamua's estimated trajectory took it about 2 light years from the star about 1 million years ago. Another of the finalists, HD 292249, a star more similar to our sun, might have had a close encounter 3.8 million years ago, but with a lower relative speed. The other candidates have higher relative speeds and distances that seemed more unlikely. So the third data release is expected in 2021 and will include 10 times as many stars, providing more candidates whose speed and trajectory might be a better match. So, interesting observations. There's probably not going to be many more observations because it's so dim and it's heading out. And they're expected to be very rare, these interstellar objects coming through the solar system. But astronomers are going to be on the lookout for them. They do expect them to come through every now and again. So a very enigmatic object, to say the least. And that brings me to end. Thank you for your attention.
Great, thank you very much, Al. All right, up next we've got Paul, and he's going to give us a rundown of the Tekla 500mm Schmidt category lens. All right, Paul.
I don't know, maybe that asteroid was firing thrusters. Hi everybody, hope everybody's doing well. I hope you got a chance to get out and do some imaging or just observing in September. We certainly had some nice nights when we weren't busy dodging tornadoes. But, yeah, hopefully we'll get some nice nights in October and November before the white stuff falls. But that also means that Christmas is getting close. And speaking of Christmas, I'm doing a review tonight on something that you've heard of a couple of times already from a few of us there, and something that I've been asked questions about, and that's the Tekla 500mm catadioptric lens. For those of you that like to peruse online catalogs at sites like OPT and Astromart, I'm sure there's a couple of you in there. You've probably seen the ads for this thing, looking something like that. And certainly the price tag on it is rather attractive for what it is. This is a mirror lens. These have been around for a long time. And as you see, 119 US. Terra Revarsky was the first one to sort of bring this one into the club there, and he did that at the beginning of this year and showed us some kind of cool pictures, which I'm going to repeat in my review here. And as a result, a few other of us decided to pop for this to see just what it was like. I mean, for 120 bucks, and we actually got, what was it, 99 bucks? I think it was, yeah. 99 bucks US. If it's a total dog, it's not too much of a loss there. So what I'm going to do is just show you what this lens is and talk a bit about the pros and cons that I've discovered in case some of you are thinking about Christmas gifts for yourself or others, right? What this lens is basically a small Schmidt-Cassegrain telescope that you put on your camera. So you can see in this cutaway view, the primary mirror is about 3.1 inches in diameter. It has a corrector plate in the front, and I did bring it, by the way, for anybody that's interested in having a look at it during the break or afterwards. Has a corrector plate in the front, just like a Schmidt-Cassegrain telescope, and a secondary mirror attached to the back of that. So your light comes in, bounces off the secondary, and through a hole in the primary to your camera sensor mounted back here. Pretty straightforward, pretty much like a Schmidt-Cassegrain telescope, or even an Edge HD with the corrective lenses on the tail end of it. So what I discovered with this, there are pros and cons like everything else. 500 millimeter focal length is quite nice because it gives you a nice level of magnification and a fairly tight field there, so it's very suitable for certain sized objects. It's moderately fast, f6.3, it's not blinding, you're not going to use this as a sports lens or anything, but f6.3 is certainly faster than most Schmidt-Cassegrains. It's very light in weight, like a pound and a half. 500 millimeters. I'm sure for those of you that are into telephoto lenses, you know how heavy they can get with glass lens. So yeah, nice lightweight, which means you can track it fairly easily, even on a really small mount. I've done extended exposures on this with this camera, with this lens just sitting on a camera on the Star Adventurer. So yeah, the payload is well within the capacity of that. Cost, as already mentioned, is pretty reasonable. I cite focusing in two areas, both pro and con. The focusing itself is actually quite smooth. There's not like a lot of slop in it, but it's stiff. It's quite stiff, and for a telephoto lens, that can be a bit of an issue because if you're having to apply a bit of force to get it to focus, you're viewing your live view, or if you're looking through the viewfinder, it tends to get pretty jittery. So, but more on that in a minute. The optics are fully multi-coated according to the manufacturer, so that gets away with it deals with a lot of reflection and such. It has a metal body, which is also nice. It's not plastic, and it has a T-mount on the end of it, which means that when you order your camera, if the place that you're buying it from doesn't supply a T-mount, you'll have to get one. Where we got it through Amazon, that was part of the deal. You just specified the camera make that you have, and the T-mount was shipped with it. And some vendors, including the one that we were dealing with, Amazon, also supply a 2-power teleconverter. And I thought, oh, okay, for that money, why not? 2-power teleconverter basically ups the focal length to 1,000 millimeters, but it's down at now at 12.6, more typical of a max Cassegrain telescope. Anyway, I was wondering, I wasn't sure how good that would be. Certainly, I've paid about $500 for a teleconverter for my Canon lenses, so if they're throwing it in on a $120 lens, I'm thinking, okay. But I'll show you some images. So those are the pros. The cons, what I found, what a number of us found that have been using this lens, is that the optics appear to be a bit pinched. Unlike a Schmidt-Cassegrain telescope where the primary mirror moves up and down to achieve focus, in this lens, the primary mirror is fixed. It's fixed, and it's the forward part of the barrel, in other words, the part that contains the secondary and a corrector lens, that moves when you try to bring it in focus. So I think my guess here is that the primary is in there pretty snugly, and as a result, probably a bit pinched on the sides there, enough to cause some distortion, even at best focus. So that problem may also be a little bit exacerbated in cold conditions. I found that in cold weather, the pinching seems to be a bit worse. So that, again, suggests to me that the mirror is being is a little too tight. Unfortunately, there's no way you can amplify that. The stiff focus that I mentioned is smooth. As I say, it's a smooth motion, but it is stiff. But it makes precision focusing for astronomical imaging rather difficult, because with this lens, as in many lenses, if you look at the marks on your lens, you'll notice that there's a fair bit of barrel movement when you're shooting at something close. Okay, so it's fairly easy to bring something close into very precise focus. As you turn towards infinity with this and other lenses, you'll notice that the distances between the mark ranges become smaller and smaller, which means that the sweet spot to get perfect focus also gets very, very small. So if you're dealing with a stiff focuser and you're trying to hit that one spot where the stars are as tight as possible, it can get a bit problematic. There is a way around that, and I'll show you that in a second. The other con that I thought was it will accept filters in the back end of the lens, but unfortunately they're 34 millimeter threads, which is slightly bigger than standard 1 1/4 inch astro filters that we're used to. So unless you want to wrap something around the threads of your 125, that's not going to fit in there nicely. It has no dew shield, no con, but also easy to make, and highly recommended because especially at this time of the year, your corrective plate will fog up pretty quickly unless you try to mitigate that dew. So the last 3 points on the con side, I'm going to show you what they mean by ways of examples. I've got a number of examples that I shot just to give you a feel for what this thing does. Generally, because of the nature of the design of the lens, it has a central obstruction, which means that you lose a bit of contrast compared to a glass lens without an obstruction. So generally lower contrast, but again, image processing can help that. It has an extremely narrow depth of field. At 6.3, there's no aperture. It's a fully manual lens. The only thing that you can adjust on that is the focus. There's no aperture adjustment, and there's certainly no autofocus or anything like that. So at f6.3, the depth of field is pretty narrow, and that has some interesting consequences especially when you do terrestrial imaging. It's not really much of a factor for astro imaging, but terrestrial imaging is a little bit of a different matter. And linked to that is the shape of what we call the bokeh, or out-of-focus highlights that are beyond the field of the sharp depth of field. So, pros and cons, and I'll show you some examples. So, I've got some terrestrial examples. I haven't processed any of these because I wanted to show you what the lens is capable of, just basically out of box. So, this little guy, I photographed him in my front lawn. He was having a snack and he was very patient and just posed there, which is good because you really need a tripod if you're going to shoot this terrestrially with this lens. It's a long focal length, and like I said, it's only moderately fast, so unless you're shooting at really high ISO speeds, you're bound to get a little bit jitter if you're trying to follow something. But he was very cooperative, and you can see with in this particular example, there's not a lot of depth of field to begin with, right? I basically shot him when he close to where you're sitting here. The background gets a little bit farther away, so the out of focus highlights are acceptable. I would find that acceptable, and I could process that into a pretty decent image. Same thing with flowers. I again shot it with a tripod. The background foliage is not too far behind these flowers. So again, the out of focus effect, not too bad. But you'll see that increases in the next one. There you see. So the background foliage here is a bit farther back, meaning that it's going to be more out of focus. And what you see, what we refer to as the bokeh. Many professional photographers and people generally don't find that very, very aesthetic. They're used to more blurred, softer, out-of-focus highlights with glass lenses. And you can see if you get a highlight there, you get a torus shape, a donut shape. Again, that's due to the central obstruction. But still, the lens does actually focus really, really sharply. I was pleasantly surprised at how sharp you could get it, again, given the very reasonable price of this lens. This guy, this mom and baby also shot in my backyard. I have a lot of critters wandering through there. Again, they were very cooperative. They were just munching away near my observatory, so I had my tripod set up, and I shot a pile of pictures, and certainly liked that one the best. But again, you can see the foliage behind the deer is quite a ways away, and you can see again the effect of the blurred central obstruction there, giving you kind of it's not a smooth flowing kind of out of focusness. It's more distinct, and personally I find it distracting. So I wouldn't keep it as it is. I wouldn't send this to National Geographic. I'll use my glass lenses for that. But anyway, again, it can produce a reasonably sharp picture, especially if your subjects are very cooperative. So, as I mentioned, it also comes with a 2-power teleconverter. Now this, I thought, for that money, is going to be probably a piece of junk. Certainly when you get something like for your Nikon or for your Canon, these are multiple elements teleconverters, usually 6 or 7 lenses in the group. Very precision stuff, and you're paying $400 or $500 for just the converter. So this was thrown in, I thought, okay, well, we'll give it a test anyway, why not? And again, I was actually surprised that at how reasonably sharp you could get things in focus, but again, a very, very narrow field of view. You can see along the stems, you can see certain little hair there and details in the buds here. But again, all the other focus stuff, you get the circular looking bokeh with that. Still, not too bad. So that's terrestrial photography. As I said, all of those were unprocessed because I wanted to give you just a feel for what it's capable of. You may have noticed in the last slide that this gadgety thing. Well, this was my solution for one of the biggest cons I had with this lens, and that's the stiff focusing. So for astrophotography, depth of field doesn't really concern us, right? Because essentially everything is at infinity. So you want to hit the sweet spot. There is one sweet spot, and it's very, very, very specific on the lens. In other words, it doesn't take too much movement of the barrel one way or another to take your stars from being as focused as they can be to being noticeably out of focus. And with a stiff focus like that, trying to find that sweet spot by hand is extremely challenging and frustrating. So what I did is I modified it. I built this, just parts I had on hand. I built this focusing attachment, which is designed to be used at near the infinity mark. It has a limited range of applicability, so I've just positioned it so that when I'm doing astrophotography with it, I can actually dial in that sweet spot. And just by using the mechanical advantage of the screw and a bit of knob there, I can make very tiny adjustments, not jiggle the camera all the hell, and pin down that sweet spot much finer than I could possibly do by hand. You can see it's a very simple gadget, just a couple of gear clamps, a couple of bolts, T-nuts, and things like that. And again, if anybody's interested in this or have already purchased a camera and would be interested in that, just drop me an email and I'll send you some photographs with some specs on it. Anyway, this gadget allowed me to do a lot better job of focusing than my first test where I was trying to focus it manually. So again, these are single, unprocessed, unstacked shots out of the can, and you can see the black area and the gray bars there. So the black area is the full field. I wanted to show you the full field without cropping, no zooming in here. So at 500 millimeters, this is what the lens catches. And I thought, well, try the teleconverter too, since I have it. And again, I was actually surprised. I mean, it's not crispy sharp or anything. Certainly what you could do is stack a bunch of these and do processing, unsharp masking or high pass filtering, and you would lift out a lot of detail. So again, this is just a single shot with the teleconverter running. So running at 1,000 millimeters, and again, that's the full thing that you get with an APS crop sensor. Okay, that's the main. So that focusing attachment is really, I find it's a necessity because of the problems that you'll see if you try to zoom in. So here's a shot of the Ring Nebula. You can see it there, tiny object. This is not the type size of object you want to shoot with this lens, right? You've got a nice field of view, and you can see the stars look reasonably good, but a tiny object. And if you zoom in on that, say if we want to look at it at 100% scale, right, which means you're not going to see the whole image, you're essentially zooming in at a factor of about 3. You can see the problems that you start to get with that. You can see the stars are spiky, and this is as sharp as I could get the focus after much fooling around with it. So 100%. And again, if you zoom it in, if you want to zoom it in even further, 200%, you can see, again, just a single image, 30-second exposure on this. With creative image processing, you can mitigate some of this, but certainly it wouldn't be my lens of choice for doing close crops on something. Okay? That all being said, my last 4 examples of images that I have for you are what you can do with this lens if you do some image stacking and if you do some image processing and if you use the full frame that you capture with not much cropping, because as you see, it's not very forgiving on the cropping. So I've got a couple here. Speaking of, there we go. Speaking of Comet 21P. So this I showed you just at the tail end of last month. This is from September the 5th. A nice comet there is now moving away from the Earth and getting dimmer and dimmer. So this was at around the time when it was at its closest approach. And again, full field, 500 millimeters. Not a bad field of view for this object. Again, you've got to determine what it is you want to shoot with a lens like this and see if it's appropriate in terms of its size. So and again, you can see at this scale, the stars aren't bad. Like if you've got really sharp eyes and you look really closely, you'll start to see where, oh, that one doesn't look quite round, blah, blah, blah. But overall, not too bad. This is a stack of five minute and a half exposures there, so kept it fairly short. And again, f6.3, not too bad in terms of speed for a lens. Like you can capture a lot in a reasonably short period of time. Next one, this is from Terra, one of the images that I think you showed that first sort of got us thinking about this lens here. So Andromeda Galaxy, and again, nice big object, so it really lends itself to that 500 millimeter field of view. Let's see, one kind of there as well, and yeah, nice detail there. This is of course a stacked image, and again, with some processing, you can again mitigate the effects of those somewhat funky stars. Another one by Terra there, the Lagoon Nebula there, nice detail. So you can see you've got nice penetration on the faint stuff. It goes fairly deep. Terra, I forget how long this was.
40 minutes.
Sorry?
40 minutes.
40 minutes. So a 40-minute combined exposure, and again, that helps you with some of the pointy stuff there. So yeah. 500 millimeters, not bad. The last one I have for you is one I shot just after the winter started breaking well, a couple months ago. But I wanted to test it to see if I was seeing a worse effect when this lens was cold, and I shot this on a warmer night. This is a stack of 5 10-minute exposures, so a fairly long exposure there. But again, you can see at this scale, when you're using the whole thing, it's not bad. For the price, it's certainly not bad. And as I say, you don't need a big heavy mount to drive this thing. I haven't tested it yet on an Optron Sky Tracker. That might be pushing it a bit, but certainly something like the Star Adventure or that class of mount, more than capable of driving something like this. So that's my review. That's my 2 cents worth on this. Be your own judge, and Merry Christmas.
Does anyone have any questions for Paul? We do have a couple minutes. You can field maybe 1 or 2.
Around 10. What's that?
Yeah.
Well, I'm just wondering, in dealing with the focusing issue on there, were you doing it through the viewfinder or using
Live view. Live view for sure. What I do with this, again, because it's pretty twitchy, you're not going to see the nebulosity through your live view. What I typically do is I point the camera at a reasonably bright star that's close to my target, and then use the live view to focus that, and also it can use it in conjunction with like a Badenoff mask. So I pin the focus down there, and then once I'm happy with it, again, because the focus is rather stiff on it, it seems to hold quite well after you've settled on a position. So once you've bingoed your star like that and got it nice and tight, then you move off to your target and do your thing.
How's its chromatic aberration, say, compared to an ED lens or a Apple?
It's not bad, again, because you're using mirrors as opposed to the lenses, except for the correctors.
There's several corrector lenses.
Yeah, there are several correctors. I didn't find it too bad. I find the atmospheric dispersion that you get when you're shooting at lower elevations is much more of an annoyance than any chromatic aberration that you see on the stars there. That might, if you're shooting really bright stars there, you've got a couple in that field in there, and it wasn't too bad, I found. Okay.
Anyone else?
So just a real question, how much are you going to use it, Paul?
Well, that's a good question. Again, it depends on what you're shooting. Often, if there's an interesting target like a comet, I like to shoot with, when I go out and do this, I'll set up a couple of different cameras so I get different scales on it. And I would, again, if I'm using this at the full frame, I would certainly put that on like a tracking platform and bag it at 500 millimeters. At the same time, I might be shooting with something that's longer or wider or shorter, depending on the specific object. So it really does depend on the object. But 500 millimeters it's a nice kind of transitional focal length between your typical telephoto lenses and your telescopes. It kind of fills that void in between. And if you're looking to spend like, you know, if you want like a Canon 400 millimeter or something like that, be prepared to ante up a lot more than this thing.
Yeah. Personally, I've actually repurposed mine as a
Right.
guide scope for my 8-inch edge. I have a refractor that sits at about 400 millimeters, so it's pretty close in focal length. And usually it'd be better to use that scope.
Have you tried that yet?
I haven't had a chance yet, but it's sitting in its rings waiting for clear skies.
There's an update in the works, I can see. But yeah, if anybody wants to see this or the focusing mechanism, just hit me at the break there or afterwards, and you're more than welcome to have a peek.
Great. Thank you so much, Paul.
You're welcome.
All right. So we have our annual dinner meeting coming up on November 30th. There are tickets for sale that are being sold before the meeting, and we'll also be selling at the break. They're $45 a piece, $46.25 if you're paying via credit. And we're having Professor Jan Cannon from the University of Western Ontario giving us the talk. Mike, do you have any? Do you want to come and speak about his presentation at all? Or?
Just the only thing I'd say, I think I'll just say from here, off, if that's okay.
Can't hear you, Mike.
All right. So for those of you who don't know who haven't been to one of these events, this is our annual dinner that we hold every year. And we typically have a speaker at the annual dinner. It's an opportunity for us to get together and you know, outside of this meeting, outside of the star parties and so forth, and chat about what we all like. I'm really excited about this speaker, Jan Cannon. He's going to be it's an old topic, but revisit it. And I think it's are we alone in the universe? And what he's looking at is various techniques. What have we learned over time? What are some of the emerging techniques for detecting if there's life elsewhere? So everyone's welcome. Open to RASC members and guests. Okay.
Great, thank you so much. And as always, it's going to be at Algonquin College and catered by them. And the food has been excellent in the past, and I'm sure it will continue to be so. So we hope to see as many people as possible there. Calendars are also for sale. They're $16 for one, or $15 each for more than one. All right, I'm going to ask Gordon to come up. He's got an update on the Fred Loss Center project.
Good evening. So, those of you who've been around for a while may remember that we used to have a key feed for the observatory for those that were trained on a 16-inch. And when we transitioned to the 18, we did away with the key feed while we were doing all the renovations. Party's over. We're going to start charging the key fee again. We're reinstating it. It's going to be $30 a year. So it's lower than it was before. The key fee, we want to begin charging it the day after the December meeting. So you've got all this month and all of next month to scratch together. In this case, it'll be $25, so we're going to prorate it. We're trying to get everything to line up on the fiscal year, which ends
September 30th.
September 30th. Okay? So your $25 will see you from now through to the end of September next year. So anybody who's been trained on the Star Master who paid the fees is eligible. We've changed the lock. We've put in a digital lock, which is very similar to the one that's on the warm room for anyone who's used that. And
Each person will be assigned their own individual code. Key codes will be active until end of September. And the fees can be paid either by electronic transfer, email to the treasurer at ottawa.rasc.ca. That email is still working?
Yep.
Okay, I have no problem with it anyway. Cash, we always accept cash and checks available to RASC Ottawa Center. And Dave is saying he's also accepting goats and chickens.
Chicken?
Yeah. Now, it's payable anytime between now and December. The December meeting, we'll change it the day after the meeting. Fees paid after March 31st will be prorated to include the following year. In other words, it's not going to be $15, it's going to be $45. Okay? Because we're trying to encourage people to use it for the whole year. And Dave will be available at the November meeting for anybody who wants to pay directly for that. I want to make a quick comment. The last members FLO or Star Party we did at Plevna, and those of you who weren't there missed a really good sky. It was really great. We're going to do some more. There are requests to do more out there. So we'll probably do 2 or 3 a year. Next Star Party is next weekend at the FLO, and I hope a lot of you will make it out to that. For those of you who've been coming fairly regularly for the past few years, we've got a bit of a tradition going. My daughter Julia and my son Andrew are selling chocolates at the break. School fundraiser. They sell out fast, so line up early. Thanks.
Gordon?
Yeah.
Loaded question. Remind me, if you want to use the flow site without using the telescope, just using the site with your own telescope, do you need to pay a fee?
No, there's no fee to use the site, and because of the lock arrangement that we've instituted, you now have access to the warm room when you go out with your own equipment. Okay, so you don't need to be trained, and you don't need. There's no fee involved. So you've got the warm room and bring your own equipment. Okay, and if anybody needs the combination, just come see me or ask one of your neighbors. I'm sure they know. It's the same as the gate combination.
Gordon?
Yes.
How do we arrange for training on the Starlabs?
Contact. That's a good question. Rick normally does most of the training, and he's traveling for about 5 weeks, leaving this weekend, I think. So he won't be back till November. But if you email, what is it, director? FLO? It's on the website. It's on the website. I think it's FLO director or RASC.O, whatever it is.
We'll get the address at the break and have it.
Anyway, if you email them, they'll set it up. Okay? But I know there's someone who can do the training while Rick's away, but I don't know if he's set that up with Dave or not. And Dave's away for the Thanksgiving weekend. So. Okay?
Thank you very much, Gordon.
All right, so we were going to go to break, but we're running a little bit ahead of schedule. We're going to pull up a couple of the observation reports for this. Then we'll go to break. All right, so Jim, Damien, and Taras. Just come up. There's lots of observers today, so let's put them up. It'll work a little more.
Lasers.
Hi everybody. Well, summer is coming to an end, and I'm going to miss a couple of So I'm going to be missing, and I guess all of you as well, are going to be missing some of the summer treats that we have in the constellation Sagittarius.
So this is a close-up of the Trifid Nebula, Messier 20, which is approximately 5,200 light years away. And M20 is an emission nebula, which is a nebula formed of ionized gases that emit light of various wavelengths. And in this case, this is an H2 region, which signifies ionized hydrogen, which gives off the reddish hue that you see in the photo. At the top of the image, you see a blue-green portion, which is actually a reflection nebula, which is not really part of M20, but it's superimposed. It kind of lays in conjunction with the nebula itself. And this is interstellar dust that is reflecting starlight. And in addition to that, there's also dark nebula, which shows the apparent dark gaps that is caused by thick dust and interstellar material that blocks light and actually creates the lobes of the trifid that you're seeing. Okay. So this is the Omega Nebula, also known as the Swan Nebula, Messier 17. And it's also an H2 region in the constellation Sagittarius. And it is one of the brightest and most massive star-forming regions of our galaxy. And there is an open, as something I didn't realize, there's an open cluster of stars, NGC 6618, which is embedded in the center of the nebula that is contributing to the ionization of the gases that we see. And lastly, this is a wide-angle image of the Lagoon Nebula, or Messier 8, which is also classified as an emission nebula and an H2 region in Sagittarius. Thank you.
Thank you, Jim. All right, up next I think we have Damien.
Hi everyone, this is my first time speaking, I guess. I just recently got back into astronomy and picked up astrophotography. So this is the second shot, really like my second real attempt at astrophotography. So that is M27, the Dumbbell Nebula. It was my submission for the beginner category for the September shooting challenge. This was taken just outside of Carleton Place, behind the hockey arena, actually, to get away from light pollution. It's taken with an 80 millimeter doublet, with 510 millimeter focal length. I had about an hour's worth of exposures. I had to throw away about 2/3 of them because of tracking errors. I since have invested in an auto banning setup. So this is a planetary nebula. It's what happens when stars and I used to know this, about 1.4 solar masses, when they reach the end of their lives instead of blowing up. And in supernova, they just kind of expand in their envelopes that go. Then there's a white dwarf that gets left in the center. Yeah, I'm still really new at post-processing images, so if you have any tips, please let me know. Yeah. That's a fantastic image for a second stab at astrophotography. That's amazing. All right, Tess.
Perseids present to
Padma with a group of guys and pointed my camera at the center of Perseus, hoping to catch some meteorites. It didn't happen. So they were everywhere, but not in my shot. I waited for 2 hours.
Murphy's Law.
Didn't get much, except a very small one here. There was doing, I can't even see it on the screen. So here.
Top left.
Oh, yeah, one over here. That's it.
And another one.
So instead, I still decided to show this picture because there are other objects which are quite amazing that showed up. Of course, we recognize the Pleiades here, double cluster. And there is a Heart and Soul Nebula. So, California Nebula, shape of California state. So I thought, well, even though there was no meteorites, but this was, in my opinion, a nice picture to share. The same night, being disappointed with meteorites, I pointed it in the opposite direction towards the west. And Cygnus was just setting, flying through the center of the only Milky Way. You can see the 2 stars, the body, the head, and 2 wings this way. And what's interesting is that this region, the Cygnus, is rich in nebula. North American nebula is one of them. Next to Teleconverter Nebula, there's also a cluster of nebula right here, if I'm not mistaken. Crescent Nebula is there, and along the wings, one of them has the shot of the veil. But describing shape like this is quite imaginable. So there is a better way of representing the constellations. There's an atlas published in London 1822 by Alexander Jameson. And what he did, each and every star of respective magnitude is pointed as a specific shape, and for the second, first, and so on, there's these different shapes. What's interesting is that if you overexpose that drawing onto a real picture, it's almost like a perfect match. So it's really amazing that an atlas made like almost 2 centuries ago still can have such a precise location as you see that the map matches here very closely, and then a video and so on.
Can you back the slide up again so we can see the video again?
I'll give it a second.
We have the Earth in
Yeah. So over here?
No.
Yeah, I was amazed with the region itself. I just pointed it, and you never know where to find it. One of the things actually, which is also in this picture, I cannot identify it, is that tag star, the one which suddenly changes the brightness. It's not explain the reason yet, but it's somewhere right here as well. So if you have a chance to just Google this atlas called Stellarium Atlas by Alexander Jameson. Has quite of these amazing representations. Comet was and still is gliding, I guess, through our skies as we speak, and this was at the peak around September 8th. So it's pretty bright. It's an image superimposed of about 10 shots, 30 seconds each, where the background is stacked separately from the comet itself, and then comet is superimposed. With the planetary camera, I pointed it at the nucleus of the comet. It's a little bit of the measurable tail. It's a very subtle difference in the brightness, but it's pointed this way. So I took a time lapse, and you can see how this was about the span of maybe 20 minutes in the distance that it traveled. So it's a black and white image, monochrome image taken with the camera. And the last picture is Mars. And Mars is getting smaller in size. This is a size difference in 3 days only. But why I wanted to show this picture, visually it's a little bit has a little bit more details than the 1.3 days before that. But there was a trick to this image. So there was an ongoing discussion, if you were following emails, about how to characterize our seeing in terms of smallest details in seconds, which an observation or an image can produce. And the suggestion was that hydrogen alpha might have such a different number of that resolution if you do through hydrogen alpha filter, which I did. So in this image, the red color, I used the hydrogen alpha. What happens, I think, is that when you do just a regular shot here above us, there's like, if you think of the sheets of transparencies, one after another, and each of them shakes and moves, and that is definitely distorting the image. But if you add a filter, then out of that pile of, let's say, 10 transparencies, only 3 will be moving and shimmering, which improves it. But when you add hydrogen alpha filter, it will be so narrow that you can think that it's only one such a sheet of books.
Yeah.
So with a narrower filter, it's much better image because I think it's only one sheet of transparency that is shaped in front of you, and it's better to get the details because the air will be laminate in that case, which added to the more details in that channel. And another trick was also that you see a little bit of outer polar cap, so which is present, which is practically not present here. So instead of blue channel, I used ultraviolet filter, and it produced some image which definitely had a pretty bright polar cap, but there was another cap at the bottom of it, which I think can be sensitive to the fact that there is perhaps a denser atmosphere or some compositions on the ground which reflect ultraviolet light differently. So whichever it is, I do give for your advice because I don't even know. I think I have to show those ultraviolet images of the planets, and they're quite amazing in fact that you don't expect to see it's there. So it's a different contrast of planet surfaces, but I don't know exactly how to interpret it. So this was the combined result of different filters and different methods of compiling them together. Thank you.
It's a really impressive planetary photography you've been doing of late. So thanks so much for submitting it for us to enjoy. All right, so we're going to go to break. Let's take about 10 minutes and then proceed with the second half. So it's 8:32. Let's get back here at 8:42. So we'll have calendars and dinner tickets for sale.
Chocolates.
Yeah, see you in 10 minutes. I'll have door prize tickets.
You want to go get the door prize tickets?
Alright, so we're going to start off the second half here with our guest, Marcus Leech, and the presentation on radio astronomy.
I forgot the bag.
Alright, thank you.
We'll get it after.
Okay.
We'll be very careful of that.
Thank you very much. My name is Marcus Leech. I've actually been here before a few years back presenting on a related subject, which was a project at Shirley's Bay Due to government vagaries, went the belly up, and we restarted again in Smiths Falls, which is where we live, a couple of years ago. We formally incorporated as a not-for-profit called the Canadian Centre for Experimental Radio Astronomy, and that is not one of our dishes. That's actually the Green Bank Telescope in West Virginia, the largest fully steerable radio telescope in the world. I emphasize fully steerable because there are radio telescopes that were larger, but they're not fully steerable. Arecibo is one of them, and then the FAST telescope in China are much, much larger. This is about 110 by 120 meters. You go up to it, you can't really comprehend the scale of it. So, many of you here, or I'm going to assume nearly all of you here, are optical astronomers of one sort or another. You have your own interests in various types of objects in the celestial pantheon. Radio astronomy is similar to optical astronomy, but at very much longer wavelengths with very different instrumentation. So visible light, as you all know, has wavelengths approximately in the region of 500 nanometers and thereabouts. From a physics standpoint, there's no difference between visible light and microwave radio. I'm going to stop turning around because I have a display in front of me. I'm not used to that. So there's really no difference. The rules of how the optics work and so on are, more or less identical. The rules of propagation and so on are identical. It's all electromagnetic radiation. It's all governed by the same physics. So as living beings, of course, we only have receptors for a tiny fraction of the electromagnetic spectrum, which is, of course, visible light. And so, we invented optical things a very long time ago, like telescopes and microscopes, because we all have eyes, and our eyes are sensitive to those wavelengths. And it wasn't until much later that we started studying the universe at other wavelengths. So, the ability to resolve fine detail is dependent to a first order on the wavelength of interest. So optical astronomy, we're used to trotting our, 8-inch optical telescopes in the backyard and resolving details, just really gorgeous details. And we've seen tonight all of the beautiful pictures we've seen here. It's because the wavelengths involved are teensy tiny, and the instruments are relatively large compared to the wavelength. So, as an example, a 10-centimeter optical telescope can resolve details that would require a radio telescope over 42 kilometers in diameter at 21 centimeters wavelength. So the differences are very, many orders of magnitude. We're not talking about one or two, we're talking many. Sensitivity is proportional to the collecting area of the reflector, though. So we both use parabolic reflectors with corrections and so on in the optical domain, and we both have to have a surface that's within 1/10 of a wavelength for a perfect parabola for a dish. Similarly, in optics, when you're grinding your mirrors, you're aiming for at least 1/10 of the notional wavelength or better when you're grinding it and then ultimately measuring it and plating it and all of the things you do. Here's a quick picture of the beam spectrum. So you've got radio, microwave, and infrared, and visible light, and UV, and X-rays, and gamma rays, and all of these wonderful electromagnetic phenomena. And you guys are in here somewhere, and we're in here. And then if you look at a breakout of that, you have wavelengths from kilometers to millimeters that we get involved with in radio astronomy. Not necessarily all of those at the CCERA, but radio astronomy in general. So, radio astronomy as a discipline was discovered by accident, like a lot of things in science. Carl Jansky in 1933 was asked by his management to figure out where these intermittent sources of static were coming from on international radio telephone circuits. Back in the day, they used HF radio to support international radio telephone traffic. Not so much these days. Back in the day when Jansky was working at Bell Labs, this was a problem. They would have intermittent noise that would go on for hours on these radio telephone circuits, and they're thinking, why? What is the cause of this? Where is it coming from? It's not the electronics. So Jansky built an antenna and discovered that the static rose and fell, measured over many weeks, with a period of 23 hours and 56 minutes, which immediately suggested that the noise was of celestial origin because it was rising and falling at a sidereal rate rather than a solar rate. So, great. So he tells his management that's what it was all about. There's his antenna, which has been rebuilt recently in the last couple of years as a historical artifact. So, it was Sagittarius, actually Sagittarius A, most notably, that was causing this issue at these long HF wavelengths. So he delivered the report to his management, then he was reassigned to other stuff, unrelated to what was probably the most amazing discovery in the history of science in the last couple of 100 years. And they said, oh, that's really cool, and they sent him off to do other things. So many years went by, and nobody really understanding the significance of his discovery, published in a few engineering magazines and so on, and everybody hummed and hawed and nodded politely. Grote Reber in Chicago was our engineer for RCA, read Jansky's work and said, hey, there's something interesting here. So he built himself a 30th edition in his backyard, just outside of Chicago. I can't remember the name of the suburb. Eventually mapped the entire Milky Way emission at 160 megahertz and produced glorious charts and maps of pretty much the entire sky visible from the northern hemisphere. And he published in the Astrophysical Journal in 1944 his results. Suddenly, they were taking this discipline seriously. Suddenly, look, there's the sky map, and it looks like, you know, there's interesting stuff there. So suddenly radio astronomy became important. There's Grote Reber's dish in the original backyard in Wheaton, Illinois. I just remembered it. And there it is, rebuilt outside the Visitor Center at NREO Green Bank in West Virginia. I'm in there somewhere. I'm not sure where, but it's a beautiful construct. It's mostly wood. The surface is steel, and they lovingly keep it preserved so that it doesn't tend to decay. So you can see some of Reber's observations there. He produced contour maps of various bits and pieces of the sky. The raw records, of course, back in the day were not computerized. They were all done on a chart recorder. So what he did was he painstakingly transcribed all of the chart recorder recordings and did analysis all by hand and produced these contour maps of the sky at 160 megahertz. And eventually 480 megahertz, but originally he wanted to do it at microwave frequencies, like 3 gigahertz, I think, but he simply couldn't get his equipment to behave adequately for the task at hand. So his experiments kept going down in frequency until he started to get results that were useful. So today, radio astronomy is pretty much cutting-edge astrophysical research. It is estimated that somewhere around 70% of what we know about the universe and its dynamics is based on radio astronomy and other non-optical wavelength observations. So optical wavelengths produce beautiful, gorgeous pictures, but the amount of science they reveal these days is less than the amount of science that is revealed at other wavelengths, infrared and millimeter wave and all the radio wavelengths and so on. So there's a lot of big projects all over the world that deal with radio astronomy. The VLA in New Mexico, I've been there, it's beautiful. Arecibo, I mentioned before, in Puerto Rico. It's a 1,000-foot dish built into an old, basically a geological formation that happened to almost have the right shape for an antenna, so they, used it and they covered it in steel and back in the 50s and built what was, until very recently, the largest radio telescope in the world. The GBT, that was on my title page there, at Green Bank, West Virginia. There's a bunch of radio telescopes there, probably a couple of dozen, various sizes for various purposes. Westerbork, Javo Bank, the millimeter array in Atacama, in Chile. Hat Creek, the square kilometer array, which is one of the major millennial projects for big science, being constructed in both the Australian outback and the southern part of South Africa. So the basic flux unit, because in radio astronomy we refer to fluxes rather than you guys might use magnitudes. We use flux measurements of any given source because a radio telescope is, a single telescope is to a first order like a single pixel photometer. So we talk about the fluxes that are arriving at the dish. So the flux unit, which is tiny, 10 to the minus 26 watts per hertz per meter squared of aperture, was named after Karl Jansky. So 1 Jansky is equal to this vanishingly small number. So how does the sky do this? Like, what are the mechanisms that allow us to observe the sky in the radio wavelengths? And there are a bunch of them, as you might expect. So blackbody radiation, which is any object that's above absolute zero, emits a spectrum of radiation from optical, infrared, and even down into the radio. So if an object is at any temperature other than zero, it has some blackbody spectrum and some amount of blackbody emission. Synchrotron radiation, a really popular one at the lower frequencies, which is caused by the interaction between electrons and magnetic fields in the interstellar medium. Then there are a whole bunch of spectral elements, dozens and dozens of them, from molecular and atomic gas clouds that are out there doing their thing. So huge chemical soup out there, more than you might realize. Formaldehyde, ethanol, methanol, and hydroxyl radicals, and all kinds of stuff out there that can be observed with microwave radio astronomy. Then there are pulsar emissions, which initially, when Jocelyn Bell discovered them, they named them LGMs because they thought it might be show the existence of little green men. But of course it wasn't. There was a well-understood, or an emergence of a well-understood mechanism for producing these pulsar emissions, and that is that neutron stars spin up. The angular momentum of the progenitor star is preserved, and these things spin up. And they also have incredibly strong magnetic fields, so they tend to produce beams of electromagnetic radiation coming from the magnetic poles. And as that beam intersects Earth, we see them as a pulse, because the beam is sweeping across our sky very rapidly. So that's what pulsars are about. Maser emissions, who would have thought it? But it turns out that in some of these molecular clouds, they are pumped by typically hot young stars that produce a lot of short wavelength emissions that pump these molecular clouds in just the right way to produce maser emission. So you get coherent, very bright spot sources within star-forming regions that are producing maser radiation at very tightly constrained wavelengths. And then there's the cosmic microwave background radiation. The leftover heat from the Big Bang pervades the entire sky. At the peak blackbody frequency, it's equivalent to about 2.77 Kelvin. And the guys who discovered that, well, there's the diagram of blackbody radiation. We already went over that. God, I've gone over all of this. Now, one of the favorite lines for me is the hydrogen line. Interstellar space is awash, if you will, for lack of a better term, in monatomic hydrogen. That is lone hydrogen atoms that are not formed into hydrogen molecules, and they're awfully lonely. And there's not, there's a few of these atoms per cubic meter, that kind of thing. However, along very long columns, very deep columns, the emission can actually be detected. Van Holst proposed the existence of the hydrogen line in interstellar space in 44, but he said, oh, we'll never detect it. It'll be too weak, which is a bit like Bill Gates saying nobody will ever need more than 640K of memory. Because in 1951, two young physicists at Harvard, using a very modest instrument, verified the existence of the hydrogen line in interstellar space. And then it was confirmed weeks later by a team in the Netherlands headed by Jan van Oort. The only reason that the team in the Netherlands failed to beat the Americans was that the team in the Netherlands, their instrumentation caught fire and they had to rebuild it. So the American team went out on that. So the emission mechanism with a 21 centimeter line is basically collisional energy transfer, which causes the electron spin to change. And when it happens, a photon gets emitted at a wavelength of 21.11 centimeters. Doesn't happen that often, anywhere between once every 100,000 to a million years. But if you look along any column that may be hundreds of light years deep, there's a lot of this going on, as it turns out, and it can be detected with relatively modest equipment these days. So a lot of you are used to hydrogen optical emissions. Very different mechanism with that. That's ionized hydrogen. This is a spin transition. So why do we care about spectral emissions, particularly the 21 centimeter line? I mean, yeah, that's interesting. But it turns out that we can use the existence of this line to take measurements through the Doppler shift of velocities. Once we can do that with a fair precision, it means we can start to understand what the dynamics of the galaxy is, and not only galaxies, but collections of galaxies and clusters, and into deep space as well. Once you have a yardstick you can use for basically producing very good measurements of motion because of the Doppler shift, it completely changes science, and that's exactly what discovering the 21 centimeter line did. So it was always a very, very important result, and it's used today. We're doing it, we have what we call a binocular spectrometer at CCERA, which is used by undergrad students at Carleton to do velocity maps of the Milky Way. Pulsar emissions. The underlying physics is still not that well understood, but we know in sort of broad general strokes how it works. Jocelyn Bell was a grad student at the time who discovered them by accident when she was going through some chart recorder data. The sort of thing that you make your grad students do. Here's 4,000 feet of chart recorder data. Please go through it and let us know if there's anything interesting. So she did, of course, because she was a good little grad student, and discovered these little bits of scruff. And that's how she described them, little bits of scruff in the record. And it was regular. There was this regular, in certain parts of the sky, every day, there were these little bits of scruff that were at a regular interval. Once every 1.4 seconds or something like that, or 1.407 seconds or something like that, there was a little tiny blip. And this was on the 78 megahertz dipole array at, was it Cambridge? Yeah, I guess it was Cambridge. So she brings it to her supervisor, and they initially call it LGMs. They started finding more of them in the data record. And, for little green men, because they had no better name for them at the time. Eventually, her PhD supervisor, Anthony Hewish, won the Nobel Prize for this discovery. Some of us feel that Jocelyn should have got the prize instead of Anthony Hewish. But it was tradition that, the professor got the Nobel Prize and the students were just, students. I mean, why do they matter? It turns out that very recently, Jocelyn Bell was recognized for having effectively been turned down for the Nobel Prize. So she got another, prestigious high cash prize decades later after her discovery was made. But she, when you see interviews of her, she's not bitter about it. She's like, well, I went on to do other really interesting things, and I've had an interesting career, so why does it matter? But still, those of us out there feel that she was cheated out of the Nobel Prize. So the pulsar rates from pulsars vary wildly, from like once every 5 seconds to several hundred pulses per second. Normally, the young pulsars are the ones with a very high spin rate. There's roughly 2,000 pulsars in the catalog. The rapidly rotating pulsars allow us to study the deep mechanisms of gravitation. I'm not quite sure exactly how, but that apparently is true. But the rapidly rotating pulsars are typically quite weak, except for one exception, which is the Crab Nebula. Interesting thing about pulsars, many of them, not all of them, but many of them are extremely precise, stable clocks. They will be producing pulses at exactly the same rate, or at a rate that is very well, at a decay rate that is very, very well characterized for thousands and thousands and thousands of years, better than any clock we can produce on Earth. So pulsars are actually used to verify precision timing sources on Earth, because that angular momentum means that the rate of spin down is very, very slow. Now, the CMB, the cosmic microwave background. George Gamow, I guess, or Gamow, in 1948 postulated the existence of the cosmic microwave background. He basically said, if the Big Bang theory is correct, there should be some background radiation left over from it. And then, in '65, 2 guys again at Bell Labs. Like, what is it about Bell Labs? But I guess they had smart people with the right equipment at the right time. And so these 2 guys, Pintjens and Wilson at Bell Labs, discovered it while calibrating satellite communications experiments in 1965. There was this excess noise, and they couldn't figure out where it was coming from. Now, 2.7K doesn't sound like a lot, but low noise receiving systems, even for satellites, at 2.7K excess noise reduces your signal to noise ratio, and so it can affect the quality of communications to satellites. So they were tasked with figuring out what was going on. Why this 2.7K excess? So they figured out that it was actually the cosmic microwave background radiation that they were observing. This thing that Gamow had postulated about in '48, they confirmed it. So they got the Nobel Prize in Physics in 1978 for this. And there's a really good book about it called, I think it's called 3 Degrees Above Absolute Zero, and it's about Pintjens and Wilson's work on the cosmic microwave background. In 2006, George Smoot received another Nobel Prize for mapping the anisotropy of the CMB, which means very tiny variations. It turns out that it's not uniform in all directions. There's slight non-uniformities in the cosmic microwave background, and this tells us about large-scale cosmology, how the universe unfolded, and how it kind of works on the very large timescales. So Smoot got the Nobel Prize for his work. He used a satellite called, I think it was WMAP, but I could be wrong. There have been a few since then. Then there are solar system objects that are, as useful for radio astronomers as they are for optical astronomers. The sun, as you might expect, is an extremely strong microwave emitter. It's basically the loudest radio source in the sky. So it makes daytime observing for weaker objects essentially impossible. One of the misconceptions that people have about radio astronomy is that, oh, you don't have to do it at night. That's not actually true in most cases. The sun can get into the side lobes of your antenna response pattern, and because it's so loud, it can completely swamp the objects that you're going to look for. So most radio astronomy is actually done at night, just like optical astronomy. The moon has a black body radiation temperature around 200 K. One of the neat things that even an amateur can do is to map the moon's microwave phase with respect to the optical phase, and they're different. because the surface of the moon is a big heat sink. So there tends to be a hysteresis in the apparent microwave temperature of the moon versus its optical phase. The lag is about 4 days, I think. Many amateurs getting into radio astronomy think that the moon radiation is just reflection of solar microwave radiation. It isn't. It's the black body radiation of the surface of the moon caused by heating. Jupiter and Io form a very interesting system for a number of reasons. In radio astronomy, Io and Jupiter have this plasma torus, which is caused by, I understand, sulfur ions that are kind of circulating between Jupiter and Io. And because of Jupiter's very strong magnetic field, and because you're dealing with sulfur ions, it actually emits synchrotron radiation, actually quite strongly at times. So you can detect that with relatively modest equipment right here on Earth. Instrumentation. Many of you look at pictures of radio telescopes and you see these massive parabolic reflectors. As I said, from a few meters to over 300 meters. The Chinese one is 500 meters across, I think. Arecibo is 300 meters across. And you have a focal plane antenna at the focus of the reflector. A chunk of waveguide, a dipole, or various other exotic little small antennas that act as your focal plane sensor, if you will. Low noise amplifiers are used. Basically, you need an amplifier whose noise is low enough to guarantee that you have adequate signal-to-noise ratio when you're trying to detect these things that are all, without exception, way down in the noise. So the lower noise of the amplifier up front, the better probability you have of detecting objects. Professional instruments, they'll chill the amplifiers with liquid helium typically, with a Joule Thompson refrigerator, multi-tens of thousands of dollars worth of refrigeration equipment. Amateurs don't usually have that option. They don't have those kind of budgets. So they use the best amplifiers that they can reasonably afford, and sometimes chill with dry ice. Now the interesting thing about developments in consumer telecom in the last 20 years is that the low noise amplifiers that you can buy for a few dollars these days are, and they operate at room temperature, nothing special in terms of environment. They operate at much lower effective noise temperatures than the exotic helium chilled amplifiers that scientists were using 20 years ago. And what that means is that the amateur can do pretty decent science because the electronics has gotten so much better. So you have a receiver chain that can do various tricks, can take various types of measurements for you, spectral measurements, total power measurements, measuring pulsars, and then you have the sort of normal back-end data processing that you guys would call stacking, for example. You might have a bunch of images of the sky and you stack them and do high-pass filtering or whatever, contrast enhancement. Radio astronomers do the same kind of thing with the raw data. They may integrate, for example, several days worth of observations to get a decent chunk of data that has low enough noise in it to take useful measurements from. Pulsar processing can take very large amounts of computing power, both because in professional circles these days, the job is to go find new pulsars. And the problem is that's a multi-dimensional search problem. You don't know what the pulsar rate is, and you don't know how far away it is. If you don't know how far away it is, it means you don't know to what degree the signal will be dispersed by the interstellar medium. So dispersion happens at the lower end of the radio spectrum, where pulses that were sent at a lower frequency arrive after the ones that are sent at a higher frequency. So if you look at all of it together as a single observation, the pulses will be spread across time and they'll smear each other out. So you have to what's called de-disperse the bandwidth that you're observing. And since you don't know how far the object is away, because you're just doing a hunt, just a blind search, so it means that you record all the raw data, and then you use computers to de-disperse the data and try to find periodic signals in your data. And you don't know what the periodicity is, you don't know what the dispersion measure is, so it means the data recording is the easy part. The post-processing can take huge amounts of computing power for weeks and weeks at a time just to find interesting stuff in the data. Total power and spectral measurements can, not always, they can require very large amounts of storage space to record the raw records that are then post-processed to produce accurate measurements, if that's what you're going after. If you want to measure the brightness of a particular object, for example, you typically need a lot of instances of measurements. You need calibrations. It all needs to be massaged together and turned into useful data that you can take measurements from. Multiple dishes, which is something that amateurs haven't actually done a lot of, which is a bit disappointing because it turns out that many of the problems using a single dish can be ameliorated by using 2 or more smaller dishes and doing interferometry, because it eliminates a lot of problems with single dishes. So if you use a lot of multiple dishes, a lot of different spacings, you can use what's called aperture synthesis to form images, just like we see in optical astronomy. Radio astronomy on a large scale, with a lot of dishes and a lot of money, produces what we would think of as images. So this one is Cygnus A, about 760 million light years away, and its features stretch around 400,000 light years. So there's the core. It's an active galactic nuclei. There's the core, and it's got these jets that are kind of barely visible, and they are superluminal, they call them. And then what happens is when they slow down enough, they start interacting with the surrounding intergalactic medium and heat it. They heat it to millions of degrees. So these lobes on the end are the heating of intergalactic gas and dust and so on when these jets encounter them. And most of the emission that the amateur can detect from Cygnus A is due to these lobes and not the core. But of course, if you're a big budget with dozens of really big dishes and lots of money, you can produce images that can image the core and the jets and everything. So that is not an optical image. That's a radio image, I think taken at 5 gigahertz, but I can't remember. There's so many, this particular object has so many different radio images of it at various wavelengths. I just can't remember what wavelength was used for this one. So, now we come to the sort of second part of the presentation. I keep banging the microphones here, sorry about that. There's the introduction to astronomy, radio astronomy, and then there's the CCERA part, so the Canadian Centre for Experimental Radio Astronomy. We formed it just over 2 years ago as a not-for-profit. I think the last time I was here, I gave a presentation on the Shirley's Bay restoration project, which was the big dish project at Shirley's Bay, which we ended up having to shut down. And spent a couple years after that looking for a suitable location and kind of a suitable plan as to what we were going to do. So we started as not-for-profit in 2016. We do educational outreach, instrument development, and sort of what I call agile experiment development. We're not dedicated to one particular project or one particular experiment. We tend to focus on things that you can complete within a season and do useful things with, as opposed to other projects out there where, for example, they have 1 or 2 very big dishes that have landed in their lap, and this happens once in a while. The money and the focus tends to turn to keeping those big dishes running and doing whatever those 2 big dishes or 1 big dish or whatever is most capable of doing, which means you miss out on a lot of speculative stuff and just changing the experiments you do on a regular basis to keep interest going. So that's what we do. That's our lab. We have about a couple hundred square feet in the Galapagos Center in Smith Falls. I don't know if any of you are familiar with the Galapagos Center, but it used to be called the Rito Regional Center. It was a care facility for handicapped adults and children too. It housed about 2,700 people at its peak. It was built in 1947, and then the government moved out of there in the late 90s, early 2000s. It went up for auction, and a guy called Joe Gallipo bought the whole place, which is 350 acres, or 350 acres and 880,000 square feet of building for $100,000. So we started sniffing around and managed to get in there, and our antennas are on the roof because the Galapagos don't want our antennas on the ground because it spoils the natural beauty or something. So, you know, you take what you can get. So we have fairly significant roof space on top of the module where our lab is. So we have antennas ranging from like little HDTV arrays to 12-foot dishes, although the 12-foot dish project ended up getting abandoned because we didn't have the infrastructure in place to haul it up to the roof and build a mount for it and so on. So I sold that for scrap. Got it for free, so why not? So the main point is that at no point, usually, there's not a massive engineering effort required to get to a point where you can start making observations. A lot of these projects in amateur radio astronomy, you'll say, oh, I'm going to build a 30-foot dish, and it's going to be great. We're going to do all kinds of really cool stuff with it. And what you do is you find that 5 or 6 years later, you still aren't making observations, the mount isn't working properly, and the people who were with you initially have lost interest because you haven't gotten to the payoff yet. So we tend to focus on stuff that can be achieved relatively quickly. You know, reconfiguration of experiments, build new ones from the parts of the old ones, that kind of thing. We have a lot of software-defined radio receivers. I first started, what would the word be, evangelizing the use of SDR in radio astronomy back around 2004, and it's only now that people are starting to really do that. So we have a lot of SDR receivers, as you'd expect, since I'm the SDR evangelist. So this is in very stark contrast to our original project, which was the 18-meter dish, just one of them, the Shirley's Bay Radio Astronomy Consortium project. It turned into a massive engineering effort that took years for us to even get to the point where we could even think about putting stuff up at the feed. It literally took us 5 years before we were able to get stuff at the feed and move the dish around so that it was aligned north-south so we could just do transit measurements. Once we got to that stage, we lost access to the site. So it was clear that that strategy was not the right thing to do for this kind of project. So now people say, oh, why don't you get, find another big dish just like it? I'm not interested because it means years and years of battling with, hardware that doesn't work anymore and 20 horsepower motors and, all the maintenance requirements and so on. You spend all your money and all your effort on one object. And it's just, for an amateur effort, it's just no good. So our current projects, we have a 611 megahertz correlation interferometer, which we're currently using to do a study of the slow decay of Cassiopeia A. Cass A is a supernova remnant. The core is not even visible anymore, but the gas cloud, of course, was heated by the initial event, but it's expanding, which means that its brightness is slowly decaying over time. The brightness decay is different at different wavelengths. We're studying it at 611 megahertz because it's an allocation that is not that well used in radio astronomy, and we kind of want to defend that band, but it's also, turns out that Cass A and Cygnus A are quite bright at that wavelength or that frequency. So what we do is the antennas are actually pointed halfway between Cygnus A and Cass A in declination, and because the antennas have a very wide field of view, they see both of them every day. And we can use Cygnus A as a standard candle against which we measure Cassiopeia A, because instrumentation varies in gain on a temperature and day-to-day basis. So if you have one source you absolutely know is rock steady, and Cygnus A is, it'll be producing exactly the same flux for the next million years at this wavelength. Whereas Cas A is very slowly decaying, probably around 0.4% per year. So if we get enough observations, we should be able to do a trend analysis of all that data and show what the decay rate is of Cassiopeia A at this wavelength. It turns out that that's TV channel 37, which was allocated in North America and the Caribbean to radio astronomy decades ago, but hardly anybody uses it. So it's important to kind of put down a fence post and say, no, we're here, don't move in on it. So that's part of the motivation for that. We have a 21 centimeter dual channel hydrogen line spectrometer. So we have two 1.2 meter dishes in their feeds. And yeah, that's one of the two antennas of the interferometer. The other one is right there, about 25 meters away. The interferometer is operating in correlation mode, which I misspelled, as it turns out. Look at that. And it uses this thing called a USRP, which is a software-defined radio made by Edis Research. We're using that one because it has two receivers that are mutually coherent. So they have the same phase view of the world all the time, which is absolutely critical to building interferometers in the radio end of things. And we use Radio as our application framework that we use for building applications. There is, there's Cassiopeia A as an interferogram. So we have the real and imaginary, or cosine sine, or whatever you want to call it, elements of the correlation. And then we just compute an envelope here, a complex envelope function, which is kind of like what you would see if you only had a single dish, like a single photometer, and this object was cruising through its beam. You would see something more or less like this. And that's Cygnus A, same thing. And there's other little bits and pieces out here, probably Cygnus X1 or something, but a little bit beyond their sensitivity. I think this is made from 2 or 3 days of data. So again, we use stacking just like you guys do to get lower noise data. And that is Virgo A, also known as M87. It's a whole lot weaker than those other two. You can see the noise level here is quite a bit higher. But again, by stacking 2 or 3 days of observation, we can get a decent detection of M87. It's about 50 million light years away. That's our hydrogen spectrometer. So the 2 dishes here, the feeds that were custom made, low noise amplifier, housing, and so on. We make all of that on site. The LNAs themselves were actually prototypes of a commercial amplifier that I've been involved in the design of. And that's the insides of our hydrogen line spectrometer. There's a couple of these AirSpy SDR receivers here. There's a precision clock source, just for the hell of it, really, because even the clocks in here are good enough for the kind of research that is being done with this. And then a couple of single board computers that process the outputs of these radios and compute average spectra, integrated spectra, and then dump it to a bigger computer for data storage. The filters, by the way, that I'm talking about here, these tubular filters, actually were pulled out of ARO decades ago, the Algonquin Radio Observatory, and Ken Tapping, because he's a notorious scrounger, when the observatory was literally tipping equipment into garbage cans to be hauled off, he intercepted a lot of useful things, including a large collection of tubular microwave filters for 21 centimeters, so he gave me a couple of them. This is a very simple, beam radio allows you to build applications kind of like Lego. This is like digital signal processing stuff. And you can sort of just plug these things together in a flow graph, and suddenly you have a piece of software that does what you want to do with the signals coming from the radio. That can either be, you know, commercial telecom type stuff, or an FM radio, or in our case, of course, it's for radio astronomy. The hydrogen line spectrometer, there's some typical results. We update live data to our website every couple of minutes, and this is, yeah, so the declination of this particular observation was around, there are two dishes, and we have them offset in declination. So at 11 degrees and 26 degrees, that's the sort of centroid RA when this image was created, and the observing bandwidth was 2.5 megahertz. So this is basically a spectrogram showing redshift here. And the zero line of the hydrogen line is right here. So you've got a couple of little features here, not very strong, and the stronger features are just above like 10 to 11 kilometers per second in redshift. So we do have a little bit of an arrangement with Carleton to provide spectral data to their undergraduate program in astrophysics, which was just started last year. After 6 months, we open source the data, but right now the raw data is, there's like a private arrangement with subscribers only, and then it's made public after 6 months. So once you have all of this data about the Doppler shift, you can calculate a rotation curve for the entire galaxy once you have enough data, and that's what they're doing. So most of that presentation I actually put together last year, but in the intervening time, we've started a new project, which is to build a phased array parabolic trough, which is a type of antenna structure that was used in radio astronomy in the old days, but then they figured out how to make really big parabolic dishes, you know, that are movable and so on. So they were abandoned for many decades. But then people like the CHIME project in Penticton decided that they were going to have a parabolic trough with phased array feed. So the thing is steerable, but mechanically it always points straight up, straight to the zenith, and the actual mechanical structure never moves. The pointing is entirely digital, as it turns out, but electronic anyway. So what that means is that you can build a fairly substantial amount of aperture that you don't have to mechanically move ever. You don't have to deal with dynamic loads and so on, so the mechanics of it are cheaper to build. And the electronics these days for building phased arrays is cheap enough that you have to do this trade-off of, do I need $1 million drive for a big dish, or do I need a $500,000 set of electronics to make it pretend to be a mechanically movable device? So this is what CHIME did. So we are doing something similar to CHIME on a much smaller scale, obviously. They had millions of dollars to spend. We have remarkably less than that. Cheaper receivers, phased array feed, no moving parts, as I've mentioned. So the first module we've already built, and it's 8 foot by 20 foot parabolic trough, and we're planning for more. Probably won't achieve that this season because the snow will start to fall, and who wants to be up on the roof building big antennas in the snow? The first module, we should be able to get it up there and at least semi-operational this season before the snow flies. There's a picture of it. So it's 20 feet, well, 19.6 feet after the curve is factored in across, and 8 feet here. The feed supports are here, and there'll be an array of 12 21 centimeter feeds up there, a bunch of electronics and computers to allow us to, the observing strategy is going to be that initially, because with phased array multi-beam instruments, you're basically no longer constrained by the receivers, you're constrained by how much compute resources you have at hand to form multiple beams. That's the other thing about phased array instruments. You can form multiple beams on the sky from the same physical object. So you're basically constrained to how much computing resources you can throw at the problem. So our initial observing strategy is going to be that we'll have one fixed beam that is always pointing at the north celestial pole, because it is relatively free of neutral hydrogen. And the other beam will basically scan the sky every few minutes. It'll just go up in declination and down in declination every few minutes and slowly build up in a mosaic of declination and right ascension in the data file. So you basically build up this image of the sky over the course of several days. And you've imaged basically about 120 degrees of declination. And so that's the plan for this. The nice thing about this design, and design is very similar to it, as it turns out there's lots of different ways you can do this, is that it's modular. Unlike a dish, adding aperture to this is very straightforward, because we just add more modules out in the north-south direction, and we add aperture. We would probably stop at 3 modules, because that gives us a more or less uniform beam shape, because it'd be 20 feet by 24 feet. So that's almost a perfectly circular beam pattern, and relatively cheap to build. This whole thing cost, I don't know, under $300 to build. Now the electronics is another question, but you can do it quite cheaply with some of the very cheap SDR receivers available these days. So probably another couple of $100 for the feed arrangement, and we already have computing resources on hand. Otherwise, you'd have to drop probably another $400 or $500 on computing resources. But it's an instrument that gives you amazing capabilities. So that's our website there. We have lots of projects and very few bodies. And you can donate time or money or whatever if you're interested. And we'd be happy to see you down there anytime. You can visit the website for contact information. Anybody who wants to come down, just give us a bit of a heads up, because we're not in the lab all the time, and we can give people tours and so on. So I'm open for questions.
Yes, we're running a little bit short on time, okay. So if you could field some questions after the meeting concludes.
Sure.
Great.
Yeah, that's fine.
And then we'll just zip along here to the next
okay.
Section.
All right. Questions after. Chris, can you pause and restart the... All right, so we're going to move on with observation reports. Jim, Damien, and Taras have already gone, so we'll start with Gordon.
Well, you've seen the trailer. This is what?
See, just the lights a little bit more, Chris?
Not too much, I'll do a little. Okay, so this is M27 dumbbell. It was photographed at Plevna using a 6-inch reflector, 750 mil focal length. And it was done with a Canon T3i. It's a stack of about 8 25-second exposures, ISO 1600. This is a nice wide field shot of M51. That's a single exposure at 108 seconds. I have no idea on processing, so I don't fool with it too much. And this one is a wider field. Jim showed you this one earlier. This is a wide field one. This one is just under 3 minutes total exposure. A stack of 7 images, 25 seconds each. Again, 1600, and again at Plevna. I was quite, the center is the top. I was quite delighted to see all of this coming a little more up here. That's it. Thank you.
need you to advance the slides there, sorry, Chris.
Yeah, this was one of the challenge objects. It's 6196, and the actual object is that one right there. But there's all kinds of galaxies in this thing. And so I just took a pen and circled some of them. And they are, nearly every smudge in there is a galaxy besides these ones, but these ones are obviously galaxies. And some of them are like 500 million light years away. So pretty deep exposure. And this one is not very long, well, it's a couple hours of exposure. This is my Comet 21P shot. It's kind of a cheat because it came up at 3 a.m. and I didn't want to get up at 3 a.m. So I took a star, and I thought it was going to go by. I was over here. I set my telescope up to start at 3 a.m. And then I woke up in the morning and put the stuff in. Anyway, it turned out pretty good. As people have mentioned before, to do comets, each image is, each color, each frame is a minute long in my example, and I probably have maybe a couple hours, 60 images in this. And as the comet starts, it starts off here and gradually goes down here, but the stars stay where they are because I'm riding on one of those stars. And so you process the comet and the stars separately and then jam them together later. So the processing is just a little bit tricky. And this is another challenge object, 6946, a galaxy called the Fireworks Galaxy. And it's called that because there's been 10 supernovae in the last 100 years. That's 10 times more than normal. And there's actually been 4 since 2002. This image shows exactly none of them. Thank you very much.
Andrew, you're next.
So tonight I have a small assortment of images taken recently and going back to the summer. I went a few evenings trying to chase down some Iridium flares before they're all replaced by the new constellation SpaceX is sending up. So this is Iridium 75 in the northern sky by Cassiopeia. If I recall correctly, it was predicted to be at the magnitude -3 or 4, so it got fairly bright. And I knew exactly where in the sky to point because it was a pretty predictable event. Set up my camera, took a few test shots, and this was captured with a 30-second exposure. My Green Nebula. Okay, so I captured this on August 5th at Rock Mountain's Video Astronomy Star Party. It's a total of an hour and 40 minutes with 5-minute exposures. It's 20 exposures. Yeah, so it's fairly small, so I have to blow up here showing the central white dwarf. And indeed, there is a little star in line of sight there as well, which is often difficult to spot. But it really turned out pretty well. It's also the last image I captured was my old setup. It was an 8-inch Newtonian reflector. I've since upgraded now to an 8-inch Richard Cruikshank. So I'm expecting some really good results with that. First of which is my version of the Comet 21P Geodesini Designer from Foymount on September 9th. I captured about an hour, but I used only 40 minutes because I was getting it to the early morning. using 2-minute exposures. Oh yeah, so it was at the time, it was at a distance of 58.6 million kilometers. And the comet has an orbital period of about 6.6 years. It passes relatively close to the Earth and then swims back out towards Jupiter. And this was a particularly close path, so it was fairly bright. First portion of this time lapse highlights the motion of the comet. And now this version, because the comet is stationary, you can pick up a few more results as well. There are various methods for stacking comets and viewing separately. But, so this is kind of a composite as well. My first image comet. Happy with how that turned out. Oh yes, and this was while it was located in the constellation Ariba. Right about at its brightest point, it's now moving away and getting fainter. I think it's about half as bright now as it was when I took this a few weeks ago. All right, that's it. Thank you.
Great, thanks so much, Andrew. Next, we've got Paul.
Hi again, just a couple of shots for you tonight from the challenge objects that were posed. This is a view of the Mount Nebula M27. What I wanted to do is show you this. This is one I took a while back, but it was at the same scale of a bit more recent work. I wanted to do this in narrowband as well. So this is broadband stuff, classic RGB, and if we look at the narrowband stuff, that's the using the Hubble palette of mapping the narrowband filters of sulfur 2, hydrogen alpha, and oxygen 3 to RGB colors. And I like this one because what got me going on this one was a close-in shot that the Hubble took of the same region. Obviously, it's the same palette there. So there's my image on top, and you can see the Hubble view and the beautiful detail that it recorded there. These nodules and condensations within the actual cloud. They're not really well understood how those form there, but wow, resolution of the Hubble is pretty amazing there. But it's kind of cool when you think that at the amateur level we have access to the same type of filters that's used in the world's premier telescope, and we can relate to what we see with the much more detailed stuff of Hubble. So that's narrowband. And the last one I have for you is that one. That's the straight wall. That was shot with a 6-inch Matsukoff Cassegrain telescope, so a fairly small telescope, but very stable night. It's pretty much at the resolution limit of that instrument. The straight wall was a challenge object. This is a ridge. It used to, many years ago, was thought to be quite steep, but it's actually not. It's only about a 6 or 7 degree slope, which is about like that off the vertical. It's about 2.5 kilometers wide, and the difference in elevation between the lowest part and the highest part is only about on the order of 240 to 300 meters over the 2.5 kilometer width of that ridge. The ridge itself extends for about 110, 120 kilometers down that way, and in this image you can see there's a lot of very small craters. I would say it was a good night when down near the resolution limit. So the smallest craters that you can see here are on the order of about 1.3 kilometers to 1.5 kilometers. The other interesting feature is this guy, Rima Bird. This is a ridge, but that's a rill. So it's actually like a little valley. It's about 50 kilometers in length. So picture about the distance from here to FLO. And it's about just about a kilometer and a half wide there. So this was done by stacking 67 frames of a video shot through that telescope. So that's a straight wall. Thank you.
Thank you, Paul. a fantastic image. All right, the last one is from me. This is the Heart Nebula. It's in Cassiopeia. I imaged it with my Skywatcher Equinox 80E and my Canon 60D8. So 2.5 hours of exposure, stacked 5-minute sub-exposures, and all processing pixels.
Nice shot, Oscar.
All right, so the observing challenge, because we're short on time, I don't have the individual slides, just the lists, but I'll email out the all the details to the email list. So these are last month's challenges, M27, NGC 6946, 6196, and Lucas Recta. Thank you those of you who participated and submitted observations. For this month, the beginner challenge will be M31. The intermediate challenge will be NGC 6888. The advanced challenge will be Stefan's Quintet, which I've misspelled. The lunar challenge will be Mons Hadley and Rima Hadley. So I'll email out some more details on these through the list, and I'll get them posted on the website. The 2018 Pulp Commission Observer of the Year Award will be awarded at the annual dinner meeting on November 30th. So be sure to get your submissions to me. Whatever logbooks you've been keeping, just sort of a history of your work over the last year. And I'll go through those and see who our observer will be. You can email that to me at meetingchair@ottawa.rasc.ca. If you're on our list, you should have seen emails from me, so you can just email it there. All right, FLO Star Parties. The next one is on the 13th of October. Is that next Saturday?
Yep, next Saturday.
We also have our public star parties at the Park Library. I think there's supposed to be one tomorrow, weather permitting. Otherwise, next Friday or Saturday. All right, Rob, did you wanted to talk us through this one?
I'll make it quick. Twice a year I invite people to my observatory. Those who are frequent these meetings know, I've probably seen this slide before. It's going to be next weekend, no surprise, because that's when other star parties are being held. But for those who are interested, it's a 24-inch telescope, Newtonian Cassegrain, and so it's kind of neat to look at planets at 1,000 power. Hopefully the seeing is appropriate. So if it's clear, it's open. It's be open on Friday. On Saturday, we usually go for dinner, then gravitate back to the observatory about 8 o'clock. If you're interested in getting more information, and I think which one is it?
Up and forward.
And the bottom of this forward and back.
Forward, back, supplement.
Okay, there we go. And so the skies themselves are fairly, not great, but not too bad either. It's about an hour's drive south of Ottawa, to give you an idea of timing. And if you're interested in getting more information, so I don't take up time here, you can email me at rdick@robertdick.ca, and I'll send you more information and a map if you wish. Thank you.
All right, Estelle's pick of the month for October is Night Sky with the Naked Eye by Bob King. So if you're interested in it, be sure to see it in the library after the meeting. Here are some of the folks that help run the club. Thank you very much to them. Our meetings are recorded and posted to our website. You can access them from there. So thank you for coming. We had an audience of 92 tonight. So thank you very much. Our post-meeting will be at Grace O'Malley's on Ogilvie. And our next meeting is November 2nd. And as always, if you have observations or ideas for talks, be sure to email me at meetingchair@ottawa.rac.ca. Member benefits for joining the club: you get access to the Ted Bean Library, where you can borrow telescopes. You'll get access to our book library, to our observatory. You'll also get these publications in the mail: the Sky News, the Journal, and the Observer Center. All right, door prize time. Ah, yes. There's coffee behind me. It's not to leave the auditorium, is what I'm told, because there's a general public outside, and there's liability issues with that. All right, thank you. So I'll just call out a couple numbers. If it matches your ticket, just feel free to take one of the prizes here. 9662.
No, I have
9670.